So this week we're going to start off by looking at section 4.2, just the first part of it. And 4.2 is actually a good section to split because there's really two cases of problems. We can look at one case today, and then we can look at the other case tomorrow. So it's perfect for splitting it up. So remember, okay, when you have a rational function, that's a function that looks something like this. Could be like 2x cubed plus 4x minus 5 divided by x minus 8. Okay, you've got a polynomial in the top, polynomial at the bottom. If the top and bottom have a common factor, remember, you can end up with a discontinuity that you can't see on the calculator. Does anybody remember what we called it? A hole, right? So that would be if you graphed something like this. X squared plus 5x plus 4 divided by x plus 2. If you factor the numerator, that will factor into, plus 1. The numerator should factor into x plus 1, x plus 4. And because the numerator has the same factor in it as the denominator, you would get a hole in the graph. Okay, so keep that in mind. All right. Let's take a look at this one. Now, do the numerator and denominator have a common factor here? Yeah. What do you get if you, well, basically you're dividing the same thing in the top and in the bottom. So what should you get? 1. So this is basically going to look like this. Basically. But you guys just told me there's a common factor. So that means the graph is going to have a what? A hole. At what number? 1. Remember, the hole occurs where the denominator would be 0. So let's graph it. And actually, well, let's use this one. Let's see what we got. So I'm going to type in x minus 1 over x minus 1. And when I type it in, when the calculator comes up, I'm going to put it in parentheses. All right, so let's try x minus 1 divided by x minus 1. Okay, and I'm going to hit zoom 6. So when you look at it, it basically looks like the horizontal line y equals 1. And if somebody walked in and saw that graph, that would be a pretty reasonable thing to say looking at that. But we know, especially if you go to the table and you type in 1 for x, you get an error. Okay? Because there's a hole there. That's a divide by 0. You can get really close to 1, and it's fine. 0.9999, yep, that's good. 1.00001. In fact, the calculator even says it's 1, but remember, it's not. It's just rounding it off. Okay? So any question on that? Why we got a hole there? All right. So that's what that one looked like. How about this one? Am I going to have a hole in that graph? Yeah. Where's the hole going to be? It's still going to be at 1. Basically, this is kind of like dividing x squared by x. You're left with just x. Right? Well, if you divide x minus 1 squared by x minus 1, you're dividing two things with the same base. Right? Really, you can just subtract the exponents. And this is going to look pretty much like this. It's going to look like a line with a slope of 1 and a y-intercept at -1. But we know that there's a hole in it. So let's graph it and see what happens. Okay, so we get x minus 1 squared. Oops. Put in 1. There we go. Having some technical difficulties. All right, so x minus 1 squared divided by x minus 1. Divided by x minus 1. So it looks exactly like a line with a slope of 1 and a y-intercept of 1. If you had to graph one like this by hand, you should try to make it so I know there's a hole when I look at your graph. If I look at that, I can't tell. So what I would do is something like this. Where did we say the hole was? 1. So when x is 1, I wouldn't even draw the blue part in the middle. I would just make it look like this. So then I know there's a hole in the graph. Okay, any questions on that? Now, if I change one number, just a little bit, let's make it x minus 2. Do the numerator and denominator have common factors now? No. So the hole's going to go away. Just by changing that 1 to a 2, watch how different the graph looks. Totally different. Okay, instead of a hole at 1, it's like the graph kind of exploded apart and now it's not even connected. Well, I guess it wasn't connected before because there was a small hole. But now it's very obvious that it's discontinuous. And does anybody remember what we call what's in there? Yep. Yep, it's a vertical asymptote. This also has what we call a slant asymptote. We're not going to talk about that today. But we are going to talk about verticals and horizontals.
So, why is there holes in the graph with the
There's a hole when you have a common factor. Okay? If the numerator and denominator have a common factor, you will get a hole. If they don't, and there's a variable in the bottom, you're usually going to get an asymptote. Okay, so when you don't have a common factor, that's when you get the asymptote. Yep.
And so what happens, like, it's at 1, right? Because if you add, like, 1 to it, then it just equals 0, right?
Yeah, this particular graph has a vertical asymptote at 1 because that's what would cause you to divide by 0. Whatever causes you to divide by 0 is where the asymptote would be. No.
And same thing with the hole. It's there because it's equal to 0. Like, at that point, like, if you add the 1, and so that's where, like, the hole is.
Yep, the hole is the same thing. It's what would cause you to divide by 0.
And so what's the difference between a hole and an asymptote, other than an asymptote will always be approaching, and a hole, like, it's just like a little blip, right?
Yeah, it's like infinitely small. Yep. Now, here's a graph that if I did something like this, actually, I don't even think I need parentheses. If I put in x squared minus 1, now, technically, that should have 2 asymptotes, because I can think of 2 numbers I can plug in for x that would cause me to divide by 0. 1 squared minus 1 is 0, and negative 1 squared minus 1 is 0. So look at how this one looks. You get 2 vertical asymptotes. One at negative 1, one at positive 1. So when you do that, now the graph just broke up into 3 parts. Okay? We don't quite look at one like that. That's a little different than what we're going to do. But any question on the difference between when you get a hole and an asymptote?
Okay, so a hole is just totally different than an asymptote. A hole cannot be considered an asymptote of
No.
1.
No. For something to be an asymptote, the graph has to like curve up very sharply and never touch it. Yeah. So asymptotes always approach infinity or negative infinity.
Okay.
Sometimes, if you have a graph, they approach both infinity, or sometimes the other side may look something like this. It may curve down. It depends. No. Yeah, holes are not asymptotes. So, in that first example, okay, we kind of already went through this when people ask me questions, but there was no vertical asymptote in example 1, the original problems. I had a hole in that graph, and I have a hole in that graph. No vertical asymptotes. That hole, or another name for it, is called a removable discontinuity. Okay? The way I think of removable is it's like there's a very small problem, an extremely small problem with this graph. If we could fix just that one little spot, then we wouldn't have a hole. when you have an asymptote, that's not a removable discontinuity. Right? If you wanted to make these two graphs connected, they're not even close to being connected. Right? A removable discontinuity is kind of like, you know, I don't know, if you're thinking about like a car accident, like and you just have like a piece of dust on your car from the accident. That's very fixable, right? We can just remove that little piece of dust and the car looks perfect. Versus an asymptote, that's like your car is totaled. There's not a small fix to make these two graphs connected, right? They're very, very totally disconnected, and the fix is not removable. Okay? So removable discontinuity basically means we could just fix one little spot, and then it would look like it's connected. That's what a hole is. But that's the proper name for a hole. Yep.
So with the asymptotes and the hole, so because the hole is 0 divided by 0, if you plug in 1, and the asymptote... Like,
Well, a hole
like,
isn't
that
necessarily
line
0 divided by 0.
Because, I mean, if the denominators are both 0, like, what's the difference in the numerator that would make one be an asymptote and one be the removable discontinuity?
So it's just when there's a 0 in the denominator, not the numerator.
Right, but when, like, the asymptote is the same thing. It's like, that's how, like, you know, like, that's where the asymptote is, if it's that big, the 0
Yep.
on the denominator, but it's the same thing for the whole. So how can you tell the difference?
If you have a common factor.
It only has to be one common factor?
Mhm.
So that would be like, if you had, like, x divided by x minus 1, if you put in x, because, like, x is, like, common?
That doesn't have a common factor. This does. Now there is a common factor in the top and in the bottom. X and x. If you take that x out, I would say when you graph that, you're going to have a vertical asymptote at 1. Now if you graph this, now I would say you're going to have a hole at 1. Because now you made it a common factor.
Mathematically, what makes that, like that difference, though, like, why?
The difference, well, basically, it's almost like these two things cancel each other out. And when you divide two things when they cancel out, it's almost like it's not there because it cancels. But it doesn't completely cancel when you graph it. There's still a hole because of the divide by, because it was originally a divide by 0. So holes and asymptotes are both divide by zeros. It's just, like if you were, let's say you had something like this. I'm just writing a bunch of factors down. And I just said to you, where are the vertical asymptotes in that problem? Well, I would say -2 and 5. The hole is good. There is going to be a hole at 8, okay, because it's a common factor. So basically, graphing this is pretty much the same visually as graphing that. They're going to look exactly the same on the calculator, except there's going to be a really small hole, which you're not going to be able to see on the calculator. The only way you know a hole is there is by looking at the original problem. Yeah. Does that kind of help? Okay.
And the hole would be at -8?
Let me put this back. The hole would be at 8 because 8 minus 8 causes you to divide by 0. Yep. Now, if I do this, I just made 8 an asymptote because there are no common factors in the top and in the bottom now.
So if you had, like, do something up there for example, so like on the bottom if you had x squared, no, on the top of it if you had x squared plus 4, would that also cancel out with x plus 2 because they can multiply each other, or would that, like, what would that do?
Well, this one will be a little tricky, but if you had this, right, if we made it x squared minus 4, technically this, you would have to know is this. X squared minus 4 factors, that's not completely factored yet. So in order to see where there's a hole, you have to completely factor something. All right? So technically now this would cause there to be a hole at x plus 2. Okay? So, yeah, so in order to find holes in asymptotes, completely factor something. Other questions on that? Okay. All right, so let's look at this. So that f of x there is just an example of a rational function. Okay, when we do an actual problem, it will be something like example A. Polynomial in the top, polynomial in the bottom. Does anybody remember when we talked about EBM, end behavior model? Which term in the top is basically going to control what that graph looks like? Just the term with the biggest exponent, right there. So whatever the first term is, if it's in descending order, is basically going to control what the top looks like. What term is going to control what the bottom looks like? Yep, the first one, as long as it's in descending order. So that is the end behavior model for the bottom. Now, if you want the end behavior model for f of x, right, you guys told me the end behavior model for the numerator, and you told me it for the denominator. What do you think you would do with the two of them to find the end behavior model for f of x?
Subtract. You subtract it.
You're going to divide them, but yes, you might end up subtracting exponents because you're going to divide things with the same base. But yeah, you're going to divide them. All right? So basically, when x starts to get really big, right? I'm talking like in the millions, billions. The value of your function is basically just going to be whatever you get there divided by whatever you get there. All the other stuff after it doesn't really matter. Okay? Because the thing with the highest exponent really controls what's going to happen. Yeah, the other terms might cause little twists and turns, but think about if x was 1 billion, right? And you had a polynomial, I'll come right back to this, but like this. If you take 1 billion and square it and double it, and then you compare that to taking 1 billion, squaring it, doubling it, and minusing 1, I mean, it's basically the same number. Minusing 1 hardly does anything. Same thing here. If you take 1 billion and cube it, and then triple that number, and then you take 1 billion, you cube it, you triple it, and you add 1 billion doubled. I mean, I know it seems like 1 billion doubled is big, but compared to taking 1 billion and cubing it, adding 2 billion to something doesn't really make that much of a difference when you're doing something so much bigger before it. Hardly makes any difference at all. Okay? So that's why the term with the highest exponent controls everything. Yeah?
So, like, with that, like, I'm just curious because I don't know. What is that, like, little, I'm assuming, like, the n and the m, like, what are these?
N and m would be exponents.
No, like, beneath the constant.
Beneath the constant?
Right, because you have, like, b and an n.
Oh, that just stands like a sub 5 would be the constant in front of the fifth, the term with a coefficient of, let me say it again. A sub 5 would be the coefficient of the term that has an exponent of 5. A sub 3 would be the coefficient of the term that's the cubed term. A sub 2 would be the coefficient of the term that's squared. And then a sub 0 would really just be your constant. So it's just a naming convention for the coefficients.
If it's just a naming thing?
Yeah. Yeah. So if you had a b sub 8, that would be the coefficient of the term to the 8th power. B sub 8. Yep. So now, I said when x is 1 billion, but it could also be negative 1 billion. Basically, whenever x is large, either really, really, really positive or really, really, really negative. Okay? That's your end behavior model, okay, for the rational function. Now, Derek already said something about subtracting. Yes. When you're dividing two things with the same exponents, like 3x cubed over 2x squared, 3 divided by 2 just stays the way it is. X cubed divided by x squared is x to the first. You subtract your exponents. Okay, so that's the n minus m. This is n. This bottom is m. 3 minus 2. I mean, you can put the 1 there if you want. But yes, you'll end up subtracting lots of exponents. And remember, we want to be careful about something like this. technically, that's 3/4 x to what power? Technically, it's to the negative first. But negative exponents just mean to take the x and put it where? Just put it in the denominator. So we're going to want to think of it like that. Okay, we really don't want to think of having negative exponents in this. It's going to be confusing. So negative exponent just means put it in the bottom. Right? That's what negative exponents are.
So if it was 3x squared divided by 4x, like to the 4th power, would you put 4x squared on the bottom?
Yeah, if it was 3x squared divided by 4x to the 4th, that would be 3 over 4x squared.
Okay.
Yep. It's not wrong to write 3/4 x to the negative 2. It's just what we're going to do that's going to be confusing.
And it could also just make sense to think of it as that the bottom one just gets 2 canceled out and you just leave it instead of negatives.
If you think of it, if you don't, like Derek said, think of it as subtraction, you could also just think of it this way. And you say, oh, I got 2 x's that cancel in the top, I got 2 x's that cancel in the bottom, I'm left with 3 over 4x squared.
But when it gets really big, obviously you can't do that.
Yeah, I mean, yeah, if you had like x to the 30th and x to the 57th, I don't want to write out 57 x's and do it that way. So then I just think of the subtraction.
Why does that work? Like when you have like a negative exponent and move it to the denominator, why does that make it positive? Like, what does that do?
Well, it's really kind of like, I would think of it this way. Like, because that's 3x to the 2nd. It's kind of like, where did you have more x's to start with? So when I look at that, I say, okay, 2 minus 4 is negative 2, but I had more x's in the bottom to start with. So that's why the answer ends up in the bottom. Okay, whenever you have a variable with a power, the answer always ends up wherever you had more variables. So if you've got 2 in the top and 4 in the bottom, you're going to end up with x's in the bottom when you're done. That's just how I remember it. So it's wherever you had more to start. Okay? So any questions on how we're going to find an EBM for rational functions? All right, so let's try example. So find the EBM, and then we're going to use the EBM to find the horizontal asymptotes. Okay, I'm going to abbreviate everything. End behavior model will be EBM, horizontal asymptote, I'm just going to do HA, vertical asymptote, VA. We'll just abbreviate stuff like that. Okay, so what's my EBM of the numerator?
2 over 3x.
2. What was it originally? Just in case people don't know how we got that.
2x squared
Yep.
over 3x cubed.
Yep. I see more x's in the bottom, x cubed. So I'm going to end up with an answer with x's in the bottom. So Derek, what did you say you got?
2 over 3x.
Yes, 2 over 3x. Now, that's the EBM. To find the horizontal asymptote, okay, you take your EBM and you basically say, what happens? So this is the question. I'm not going to write this every time, but I'll write it this time. What happens to the EBM as x approaches infinity, or as x approaches negative infinity. In other words, let x get really, really big and tell me what's happening in that fraction. And what does it approach?
0.
Yeah. So as x approaches infinity, my EBM approaches 0. So that means the horizontal asymptote is y equals 0. I'm not going to write that whole explanation every single time, but that's the reason. Okay? So as x approaches infinity, actually I guess you could technically do plus or minus infinity. My end behavior model is getting a huge denominator. Right? If x is 1,000,000, 2 divided by 3,000,000. Basically 0. It's approaching 0. So remember, horizontal, you always want to write y equals. Don't put x equals, that's vertical. Okay. Any question on how we got the EBM or the horizontal asymptote?
How do you tell the difference just looking at one of whether it's going to be vertical or horizontal?
We haven't talked about the vertical yet, but it's, well, we kind of did a little in the past, but it's the zeros of the denominator. So that involves having to factor the denominator, which can be kind of a pain in a problem like that. So we wouldn't be doing vertical asymptotes on this problem. But I'll show you when we get to it. Okay, what's my end behavior model here?
2 over 3.
Yeah, basically it's the variables are going to cancel out. You had 4 x's in the top, you had 4 x's in the bottom, and you're left with 2/3. That's your end behavior model. So now, horizontal asymptote. Look at that fraction, and I want to know what happens in that fraction as x gets bigger and bigger. What does this fraction approach?
It's a constant.
It's a constant. So what does it approach?
Two-thirds.
Itself, 2/3. So when all the x's cancel out, your end behavior model is the asymptote, because it's just y equals 2/3. So if you say, well, let x get bigger and bigger, there is no x. So as x gets bigger and bigger, it doesn't matter. It's always 2/3. And in fact, if you graph that on the calculator, it would look exactly like y equals 2/3. But you would have a small hole in it, because these are common factors. You'd have a hole in the graph right at 0. You can try it. Compared to if you just type in y equals 2/3 on the calculator, it's going to look the same, but there won't be a hole at 0. Okay? So,
So when you're looking at the whole, you're not, wait, so it wouldn't be -3 because that's like the end result. It would be whatever causes 3x to the 4th to be 0, right?
yeah. I'm not going to ask you about the hole here. I just want you to be able to get the EBM, but yes.
Is
Yep.
there a function on the calculator that tells you, like, if there's a hole? in what
No.
you're doing? No.
Just if you plug it into
The table, yeah. The only thing you can do is, and I think I showed that, is you, like this one, if I look at it, I think there was a hole at 1. You have to kind of know that there's a hole there and you can check it. But the calculator itself can't tell you if you don't know. Because remember, the hole is infinitely small. So you couldn't even write a computer program that would really check for it because, I mean, let's say the hole was at 0.000000736642. I mean, it might take a computer forever to find that. So you have to know that there's a hole there. And you're not going to have one that lousy. Usually holes occur for us at like nice numbers. 1, 2, 3. Other questions?
Yeah, so you would only know that there's a hole though if you factored it all out.
Yes, you can only tell holes if you factor it. If you can't factor it, then you can't tell it. Nope. Got to be able to factor it. All right, so if I go back here for a second, you might have noticed that sometimes the exponent in the top and the bottom were the same. Sometimes the exponent in the bottom was bigger than the top. I didn't give you one where the top was bigger than the bottom. Okay? We're not going to talk about that case today. We're going to focus on when the degree in the top is equal to or smaller than the bottom. Okay, so just like the last 2 examples I gave you. So, in order to sketch these graphs, I'm going to give you a few kind of guidelines. These guidelines don't always apply. It depends on the problem. But one thing that's good to try to do is find the intercepts. Now, if a graph never crosses the x-axis or y-axis, then you're never going to find the intercept. Okay? So it kind of depends on the problem. But sometimes finding intercepts are helpful. Okay, remember the trick to find an x-intercept, you plug in 0 for y. To find a y-intercept, you plug in 0 for x. Vertical asymptotes, very important. Okay, so to find the vertical asymptotes, find where the denominator equals 0. Now, The only way that a number would not be a vertical asymptote is if it's a hole. So you've got to check, wait, is this a hole or is this an asymptote? Okay, so that involves factoring. Okay, after we get the vertical asymptotes, we're going to want a horizontal asymptote. To get that, find your EBM. Remember, find your EBM and then let x approach positive or negative infinity. Same thing is going to happen. So we're going to see this notation a lot, like the limit as x approaches a value, and that's going to be on the test as well. So this says as x approaches infinity or negative infinity. We're going to use the calculator to help us with step 4. You don't really need a graphing calculator, but the table feature of the calculator makes step 4 very quick. So if I know there's a vertical asymptote at 2, I'm going to say, okay, what's happening near 2? What's happening at like 1.999? What's happening at 2.00001? Okay? I want to check the behavior on each side of the asymptote. One of two things is always going to happen. The graph is either going to be up extremely high or down extremely low. Okay, and then after we graph it, we can always double check our graph with the calculator. Okay, but finding the asymptotes, that's probably going to be the most helpful thing because you're going to end up with something like this. And once you get all your asymptotes, it's going to kind of give you sections. And then our graph is going to pretty much stay in some of these sections. Okay? It usually takes up 3 out of the sections you would see there. Now that would be a problem for 2 vertical asymptotes. Okay, but getting those dotted lines will help us. Okay, so they want us to sketch this graph. So first step, just to notice the degree in the top is 1, the degree in the bottom is 2. So the degree in the top is definitely less than the degree of the bottom. All right, so it doesn't really matter out of these 5 things which ones you do first. Let's start with the X-Intercept. How do you find the X-Intercept again? Plug in 0 for y. Remember, this is y. F of x is just another name for y. So if we set that fraction equal to 0, we just have to solve. Well, you want a fraction to equal 0. What's the only way a fraction can ever come out to 0? If the what? If the numerator equals 0. So basically, if you can tell me when that's true, that's going to be my X-intercept of this graph. When x is 1. Only thing I want to check is, does plugging 1 in for x cause me to divide by 0? No. 1 squared minus 1 minus 6 is not 0. If it was, like if you plug in 2, what's that going to be? 4 minus 2 is, no, it still wouldn't work. I'd have to figure it out, but actually 3, right? 3 squared is 9. 9 minus 3 is 6. 6 minus 6 is 0. If 3, like if that was x minus 3 in the top, this graph wouldn't have an X-intercept. Okay? You can't plug in a number that would cause you to divide by 0 and say that's your intercept. No. Okay, but 1 does not cause you to divide by 0. So the graph is going to cross right there. By itself, that doesn't tell me very much. That's all I know. Okay, Y-intercept. So the Y-intercept is when I plug in what for what?
0 for x.
0 for x. That's usually pretty quick. What's 0 minus 1? And then 0 squared? Minus 0? Minus 6. So my Y-intercept is 1/6. So again, those 2 points are so close together, I can't even really tell what's happening. But I found them. So I got my X and my Y-intercepts. What else? Let's find the vertical asymptotes. Okay. What do I have to do to find the vertical asymptotes to the bottom? I've got to factor it. That's x minus 3, x plus 2, let me double check that, x squared. Yeah, that's how it factors. So, and you can put x minus 1 in the top if you want. So no holes in this graph, no common factors. So what are my vertical asymptotes?
3 and 2.
Yep, so let's make those. Remember, vertical, x equals. Okay, so let's put dotted lines in at those. So we've got one at 3. If I can move. There we go. So one at 3 and one at -2. And they should go on forever, but that's as tall as I made them. All right, so we've done step 1, step 2. Find the EBM. Okay, let's do that. Okay, well, what's my EBM here?
1 over x.
Yeah, the EBM is easier to tell from the original unfactored one. Okay, to get the EBM, you need the highest degree term. To find that, you'd have to FOIL this out. So we'll go back to the original. X over x squared. Now, we don't really do anything with that other than so now we're going to do the horizontal asymptote. So let x approach infinity in your EBM. What happens as x approaches infinity? Gets closer to 0. So now put a horizontal line at 0. Let's try going the other way. Okay, so that's that. Now, step 4 is what's really going to help us out. We're going to check what's happening near the asymptotes. We have 2 of them, -2 and 3. So we're going to use the table. So we have to type in our problem, use parentheses, x minus 1 divided by x squared minus x minus 6. Now, don't put in 3. I already know what's going to happen if you do that. You get an error. And don't put in -2. I want to put in values close. Okay. So what's a value that's extremely close to -2, but a little bit more negative? Like to the left of -2. -2.001. Let's see what happens. So when we are just to the left of that green asymptote, my graph is at -6,000. Okay, so it's like it's way down here. All right. Now let's check just to the right. What's a value that's just a little bigger than -2?
-1.999.
Okay, let's check that one. -1.999. Positive 600, so way, way up. Okay, so way, way up there. Now let's do the same thing near this other one. This is at 3. What's a value that's just a little smaller than 3? 2.999. And a value a little bigger? No. So when we're just before, we're way down. Just after, way up. Way down, way up. Now remember, what was our horizontal asymptote? What was our horizontal asymptote? Y equals 0. So as you head further and further left and right, this graph is going to get closer to 0. But it can never cross the dotted line. Okay? That horizontal line can never be crossed as we head further and further and further right and further and further and further left. It's going to get crossed in the middle. But horizontal asymptote is about what's happening really, really far from the middle, like as x approaches infinity. So it's going to get closer and closer to that dotted line, but never cross. And same thing here. It's going to get closer and closer to this dotted line and never cross it. So we have to connect these 2 points. And we're going to connect them with a curve. So what happens is we're extremely close. Starts getting a little further away. And now as it approaches this dotted line here that's vertical, think of it as like a wall. Right? It's like it's going to try to hit it, but then it can't. So it's like deflected down. Right? So it's going to basically curve something like that. Okay. Same thing's going to happen in the upper right. This is going to stay very close. It's going to all of a sudden start to come up, and then it hits this wall, and then it curves up. So it's trapped in those 2 sections. Now we just have to figure out what's happening in the middle, but I've got 4 dots, and we're just going to connect them with a curve. Yep.
Why is it able to cross the x-axis in the middle but not the ends?
Because remember, horizontal asymptote is all about what's happening as x gets huge. So you're looking at what's happening very far away. This horizontal asymptote means absolutely nothing in this spot at all. The only place that it's significant is when you're far, far away from the origin.
So, like, is it there?
I mean, it's there, but it has no meaning in that part of the function. It means nothing. The only place that it has any significance at all is like way out in the hallway and like way out in the woods, when it's very, very far away from the origin. Near the origin, it doesn't mean anything at all. No. So, inside here, we're very close. And then all of a sudden, this is kind of where finding the intercepts actually came in a little handy, because it's going to come down. It's going to curve through those intercepts, and it wants to keep curving to the right, but it can't. Runs into another barrier, and that kind of deflects it down, like that. And that's a pretty typical pattern for these kinds of problems. So let's hit graph and see how we get. Not bad.
Pretty good.
It's a little flatter in the middle than I think I drew it, but and that's fine. We've got the 3 main sections of it by finding the asymptotes and intercepts. Okay, so I would ask you for these kind of things on a graph. I'd ask you for the X, the Y-intercept, the verticals, the horizontals, and the EBM. Those are all the things I would ask you for. And then a sketch. Someone have a question? Yeah.
So you can cross 0 like in between.
Oh yeah, yeah. Because like that horizontal asymptote really means nothing in the middle. No. It's only significant on the extreme ends of the function. Yeah.
What if you had like 3 or 4 asymptotes, like in between each like one of those like sections, is it able to cross the x-axis?
It could. We're never going to have more than 2, so it would really depend on the function. Every function can do all kinds of different stuff. But yeah, it could definitely cross it towards the middle parts, but it would never cross it as you get further and further left and right in the kind of problems we're going to do. There are some asymptotes that it does oscillate. Like if this is an asymptote, it does something like this. But to get that kind of behavior where it's oscillating and constantly above and below, but converging to the asymptote, you'd need a trig function. That's the only way I know to do that, and we're not there yet. So no, so you won't have that.
So I'm still confused about like the approaching infinity part, like down how you got 0.
We'll do another one.
Okay.
We're gonna do another one. Pretty much, it's actually gonna look pretty much the same.
Okay.
We'll try to do 2 more if we have time, and that's all I had. Anyway, But this time I laid it all out. Verticals, horizontals, X-intercept, Y-intercept. Now, what I would probably do is I would factor this right away. No, you don't need to factor it to do everything, but some of the stuff here, it's easier to do with it factored. Some of it, like the horizontal asymptote, it's easier to do with it not factored. Okay? So, let's see if we can factor the bottom. How does the bottom factor? Or what can you factor out? Yeah.
X can be figured out.
Yeah. So all you're left with is 2x minus 5. Okay. Not really worried about the numerator at the moment. I'll worry about that when I get to the X-intercept, which I think that numerator could be kind of a pain, but we'll see. All right. So vertical asymptotes. I'm going to come right back to that. Let's do the horizontal asymptote. So to do that, first find your EBM. Okay, what's the EBM here? 3 halves. Yeah. Now, let x get really big in the EBM, and what does the EBM approach? 3 halves. Okay, so we're going to put a horizontal line at 1.5. Start with that. So 1.5, about right there. Okay, let's do the Y-intercept. To do the Y-intercept, what do I plug in?
0.
4 x. That I'm doing that because that one's easy. 0 squared times 3 is 0 plus 0 minus 4 on the top. Over, what if you plug 0 into the
0.
bottom?
0.
You get 0. So what does that mean? There is no y-intercept. Okay? Because if you plug 0 into the bottom, you get 0 minus 0, which is 0. This graph will never cross the y-axis. So it's not applicable. That's not going to help us. And that's fine. We'll do everything else that we can do, and hopefully that will help us. Yep.
Could it be like an asymptote, out of curiosity?
Well, we're going to have asymptotes, yes. We're going to have a horizontal and a vertical asymptote. But this has nothing to really do with asymptotes. It just means, well...
Because I'm like, there's something on the top, but then the bottom is 0.
Yeah.
And, like, there wasn't a common factor that
So what this basically can actually give you a hint about is if you never cross the y-axis, it probably means your graph is getting closer and closer and closer to the y-axis and never touching it.
Right.
So yeah. We're just going to try to make sure we don't have a hole there. Like that it doesn't just like skip over the axis somehow kind of weird. That usually doesn't happen, but that's what we're going to check
So
out.
we have to factor the top.
Yeah, we got to look at the top now. So I want to look at the X-intercepts. So the X-intercept is when y equals 0. Basically means make that 0, which means make the top 0. So let's set the top equal to 0. Let's see what happens. 3x squared plus x minus 4. Let's try to factor it. And if we can't,
1.
well, then we're going to have to use quadratic formula. So we've got 3x and x. My signs definitely have to be plus 4 minus 1. Let's check. 3x squared. That's not going to work. So let's try 4 and 1. Might have to fix. Wait, did I even switch them?
No.
So you just wrote the same thing again? All right. Switch the signs. Let's check it now. 3x squared minus 3x plus 4x. Yep. And 4 times 1 is negative 4. Perfect. So we didn't have to use quadratic formula. And that's supposed to be a 4. Okay. So that means this graph is going to have 2 x-intercepts. It's going to cross the x-axis in 2 different spots. This one is x equals 1. And this one is x equals negative 4/3. So x equals 1. Negative 4/3 is, what, like negative 1.3? So right about there. So it could kind of come up like a parabola and back down. We don't know. Let's see what
So
happens.
does it have to have a hole then?
Let's look at, that's why I saved the vertical asymptotes for last. You have 3x plus 4 in the top. And what was the other factor? X minus 1. Do I have any common factors in the top and in the bottom? Well, you'd have to have another x on the outside like that. That would be a common factor. So any common factors there? Nope. So there are no holes. Which means these are going to be asymptotes. And there's 2. What value would make the first factor 0?
0.
0. And the second factor?
2.5.
2.5 or 5 halves, yep. Because 2 times 2.5 is 5, 5 minus 5 is 0. Okay, so I think we've got everything, and now we're going to get to the part that Maddie asked about, is checking what's happening near the asymptotes. Okay, so let's just throw in 2 vertical lines. 0. Oops. Can't move it. Oh, can move that one. So that was at 0. And I'll just try to put it at 2.5. Is that okay? Okay, so those X-intercepts are actually in different sections. So they're not even going to be connected to each other. Okay, they're in different parts. So now we want to type it in and check what's happening near the asymptotes. Let me unstick the calculator. So I use parentheses. That's going to help. Oh, it did?
Oh dear.
Alright, so we got 3x squared plus x minus 4. Close it. Let me open it. Hopefully it just works better now. Because I need to use it from here in a minute. Divided by...
Okay, yeah, you pressed it.
This is a little
I
too...
think it's if you press and hold it, it turns red or something. I don't know.
Divided by 2x squared minus 5x. You hit graph. Actually, I don't want to hit graph. I want to go to the table. All right, so now let's pick a number that's very close to one of my asymptotes. What was one of them? 0. Sometimes when I open and close it, that helps.
It's just, well, we did 0.
You know what? We're going to go like this. I'm going to use a different calculator. That's okay. 1 second, please. Divided by 2x squared minus 5x. Okay, so now tell me what was one of our asymptotes? 0. So we want to check what's happening just to the left and just to the right. One of them is going to be up very high, the other one is down very low. Yes?
On the calculator, you forgot to put the x in before
3x squared plus...
before the 2x. Oh.
I think I...
Oh, wait. You already put it.
Is everything okay? 2x squared minus 5x?
Yeah.
Okay. All right, so what's a value that's a little smaller than 0? Very close,
0.1.
but
Negative.
smaller, negative.
Negative.
So we're basically checking what happens if you're just a little to the left of the asymptote. So a coordinate on this graph would be negative 0.0001, comma, negative 800. So if you go just to the left of the asymptote, you are way down there. Okay? Can already tell what it's going to look like. It's got to stay in this section. Staying very close, moving away a little bit, curving, and then getting closer and closer again. So that's that part. Now, let's check a value a little bigger than 0. What would be a value that's a little bigger?
0.1.
0.001. 0.1 is okay, but I go even closer. 0.01. So, just to the right of 0, 0.01, comma 80 is a point on this graph. So 0.01, comma 80, way up there. So this graph is going to curve in the middle, extremely steep. Okay, very, very steep curve. Calculator's probably going to have trouble sketching it. It's probably not going to look perfect. Keep clicking that one. The other asymptote, 2.5. What's a value just a little smaller than 2.5?
2.499.
And a value a little bigger than 2.5?
2.5001.
So, 2.499, comma, negative 3,000 is a point on this graph. So just before 2.5, way down here. Just after 2.5, way up here. So, in this section, it's going to look like this. Technically, I can put arrows on all these. I usually don't. And now the middle section, I've got 3 dots. It's going to be connected with a curve, but it's going to be very steep. So it's going to look kind of like this. Not much of a curve. I don't think you're going to see much on the calculator screen. I also think there's going to be a problem when we sketch it in here. I think all of a sudden the calculator is going to show it as stopping.
Yeah.
Because it's so steep that it's having some trouble with it. So let's hit graph. A little slower than the other one. Yeah. So that's not quite what it should look like. It should continue down forever, like ours, and up forever in the middle. That's basically the graph.
So typically that's what they're gonna look like with like the sections.
Yeah, it can look a little different, but that's pretty typical.
Okay.
Notice when your exponents were the same, the only difference between this graph and the other one is where the horizontal asymptote was. The horizontal asymptote can move off of 0 only if these exponents are the same. If the one in the bigger is bottom, try again. If the one in the bottom is bigger, the horizontal asymptote is always at 0. So in a problem like this, you're always going to end up with more x's in the bottom than you do the top. And that always means a horizontal asymptote of 0. Now, if the degree of the top is bigger, that can get a little tricky. Right? We're not going to look at that today. But what can happen there is the horizontal asymptote goes away. Okay? Best case scenario, easiest one, is you get a slant asymptote. So it's still straight, but it's on a slant. If it's not a slant, then it can get even worse. You can actually have an asymptote that's curved. So you could end up with a graph that actually does something like this. It's a graph that gets closer and closer and closer to a curved dotted line instead of a straight. We'll see that tomorrow. Okay, but any other questions on that? If I were to do that one, where would my horizontal asymptote be?
0.
It would be at 0, because the EBM would be 1 over x. To find the vertical asymptotes, what would you have to do in the bottom?
Factor.
You'd have to factor it. So is there any question how you do that one? How about, you should be able to tell me your X-Intercept. Where's your X-Intercept here? Yeah. Should be at 2, as long as 2 doesn't cause you to divide by 0. 2 squared is 4, minus 4 is 8, minus 3, now you're good. So 2 will be your X-Intercept. What's your Y-Intercept? Yeah? 2/3. Basically, when you do an intercept, when you plug in 0 for x, anything with an x just disappears. And you end up with 2/3. Okay? So the longest part of this problem would now be typing it in on a calculator that cooperates, and then checking the behavior on each side of the asymptote. But I think it's going to look just like the other two we did. Okay. Yep.
So you would have 2 X-intercepts if the numerator factors?
Yeah, if the numerator factors, you could have
like on
2.
The last one.
Yep.
So because that factored, we get 2.
Yep.
Okay.
Yeah, the numerator is already factored here, so you're only going to get 1.
Right.
So the X-intercept is
The X-intercept is when you put 0 in right here, so yes. Yep.
And you only need to find the top though for 0?
Yes, because the only way that a fraction can equal 0 is if the top is 0.
Oh, okay.
The bottom doesn't matter.
Okay, that makes sense.
Yep. All right, so homework tonight, it's not all sketching. Some of the problems are just like find the EDM or something like that. So 1 through 7 odd, 9 through 12, 15, 17 to 22, 23 to 26, 29 to 33.
Did you just write 17 to 26?
Yep, I could have. I could have written 17 to 26. Yeah. But I didn't. You caught it, which is good. Because I was just seeing if you were paying attention. It's great. Good job.
What do you want with that?